So I'm going to work through an example where I solve for probabilities for combinations of events. So I put in the notes this summary table of different terms that we've learned, their symbols, what it means in words, and then the different formulas we have for solving for their probabilities. So the first term in this table that I'll review is the complement of an event. So the complement of an event is always the opposite. Say event A is that a student is female, then the complement of event A would be that a student is male. Since those are the only two possible outcomes, the sum of their probabilities has to be 1. The probability a student is female plus the probability a student is male equals 1. So whenever you're solving for one of those probabilities individually, you can just do 1 minus the other probability. So if I tell you the probability a student is male is 0.6, then you know the probability a student is female would be 0.4, because that's just 1 minus 0.6. So then the second type is unions. So now we're combining two different events, and let's call one of them A, the other one B, and we're interested in the or, A or B. So the notation is A and then a big U, B. So that'd be like find the probability a student is female or is a sophomore. Okay, there's two different formulas to solving for that probability, the probability of A or B. And it depends on if those events are mutually exclusive or not. So the term mutually exclusive meant they have no outcomes in common. There's nothing in the sample space that would fall under both of the events. Just like the gender example, there's no students that are both male and female. So that would be mutually exclusive events. The notation for mutually exclusive would be if the probability of A intersection B equals 0. A intersection B, the upside down U stands for and, like we'll go over in a minute. So if you figure out that two events are not mutually exclusive, meaning they do have some outcomes in common, then finding the probability of their union means adding the individual probabilities and then subtracting the probability of their intersection. So if I was trying to find the probability a student is female or a sophomore, then I would have to add up the probability they're female plus the probability they're sophomore minus the probability they're female and a sophomore. Okay, but if the two events are mutually exclusive, so if I don't have any students who are females and sophomores, then this A and B probability would just be 0. So that subtraction part of the formula goes away. And we're left with the probability of A union B being just the sum of the two probabilities. So I always advise that you use this formula. The probability of A union B is the sum of the two minus the intersection. I always suggest you use that one. And then if you're working on a problem where they're mutually exclusive, then you'll just subtract 0 at the end, and you didn't do anything wrong. But if you try using this formula, the probability of A plus the probability of B, on a situation where they're not mutually exclusive, you'll forget to subtract their intersection, and you'll get the wrong answer. So it's better to just try to use this one, the addition rule. Okay, so then the next type is finding the intersection of events. Now this is again when we're talking about two events. Let's call one A, one B. But now we want to find the probability they both happen, A and B. The probability it rains today and I brought my umbrella, A intersection B. So that notation is the upside down U, this like N thing, N for and. And again, we have two different formulas for solving for that probability. Now it depends on if the two events are independent or if they're dependent. So the term independent means that just because one event happens, it doesn't affect the probability of another event happening. That would be two independent events. For example, flipping a coin. If I get a heads on the first flip, it doesn't affect what I get on the second flip. So flipping a coin, 2 flips, are independent events. Okay, dependent events is when the first event happens, it affects the probability of the next event happening. So for example, your grades in the course. Your grade on the first exam affects your total grade in the course. Those are dependent events. So if you're working on a problem where the 2 events are independent, they don't affect one another, then finding the probability of their intersection means multiplying the 2 probabilities. So I want to find the probability I get a heads on the first flip and a heads on the second flip. I would just do 0.5 times 0.5. Multiply the 2 individual probabilities. If I'm working on an example where the 2 events are dependent, so one of them affects the other one, then finding the probability of their intersection means multiplying the probability of A times the probability of B given A. Okay, so this notation right here, B, and then a vertical line A, is called a conditional probability. That brings us to the last type, a conditional probability. Here I have the notation A, vertical line B. That would be when we're looking at event A, given event B already occurred. So we're talking about dependent problems. The events affect each other. So if we already have some prior knowledge, we already have some partial information that one event occurred, then this conditional probability is now what's the effect, or what's the probability of now the second event occurring. So that formula, the probability of A given B already occurred, equals the probability of their intersection in the numerator divided by the probability of the given part in the denominator. So notice here I'm doing A, vertical line B, and then the B is the one in the denominator of the fraction. Those have to match. Whatever's to the right of the vertical line has to be in the denominator of the formula. So that's how to find conditional probabilities. So how to check if 2 events are independent, that would be if their conditional probability equals the probability of the first event, event A here. So this is saying it doesn't matter that B occurred if they're independent. The probability of A given B already occurred would still just equal the probability of A, because it doesn't matter. It didn't tell us anything new. They're independent of one another. So that summarizes some of these relationships that combining 2 events. And it can extend on to 3 events, 4 events, 5 events. But here's just a little table to summarize, just looking at 2 at a time, A or B, A and B, and then some of those terms, the difference between mutually exclusiveness and independence, and when you have to check which ones for using a certain formula. So it can get kind of confusing. It takes some practice in knowing what you need from the problem, what you're given from the problem, and what it is you're trying to find. But the purpose